Hello and welcome back to App for You. In this particular video, we are going to discuss a new problem from balanced binary tree, basically from trees. So before we proceed with the problem, let us understand what is actually a balanced binary tree. So the definition that is given here is clearly states that given a binary tree, we have to determine a height, whether a tree is height balanced or not. Now what do we mean by that? So a height balanced tree is nothing but a binary tree in which the left and the right subtree of every node differ in height by not more than 1. So in simple words, a height balanced tree or a balanced binary tree is that particular tree for which the height of the left subtree and the right subtree, the absolute difference of the left subtree height and the right subtree height, okay, is always less than or equal to 1. It will never exceed 1. Getting the point? So for every node, so please note this. So basically a balanced binary tree are those trees for which whenever you consider any node, you will find out that the height of the left subtree of that node and the right subtree of that node, you just compute them and find the difference between the height of the left subtree and the right subtree of that node. You will find out that the difference has never exceeded 1, right? So if the difference throughout the tree never exceeds 1, then you will find out that okay, your tree is basically a balanced binary tree. So the thing that is given here, the example that is given here is, you can just refer it. Basically this is the tree that is given. If you consider this node, the left subtree height is nothing but 1, the right subtree height is nothing but 2, and you find out the difference is 1. It's fine. Now if you consider this subtree, you will find, if you consider this node, the height of its left subtree is 1, the height of its right subtree is 1, the difference is nothing but 0, and it is less than equal to 1. So true. So you will find out for every node, if you compute this leaf node also, if you compute these leaf nodes, their left and right subtree are null, and their absolute difference is obviously less than or equal to 1. So they are automatically a balanced binary search tree, right? Now if you consider the second example, this particular example, you will find out that from the first node itself, if I consider this node itself, the height of the left subtree is nothing but 1, 2, 3. The height of the right subtree is nothing but 1. The absolute difference between the left height and the right height, or the absolute difference between the left subtree and the right subtree for this particular node is nothing but 3 minus 1, which is equal to 2, and this exceeds 1, right? This is greater than equal to 1. So this is not a balanced binary search tree, right? If you detect if you detect even a single circumstance where you found out that the height of the left subtree and the right subtree difference is exceeding 1, okay, it might be in this particular node itself, or even if you find that okay, somewhere here that particular rule is being violated, somewhere, suppose any point it can get violated. So if it gets violated, that is, the condition is the absolute difference between the left height and the right height should be less than equal to 1. If this condition gets violated at any point inside the subtree, then you will conclude immediately that balanced binary search tree is not possible. So this is not a balanced binary search tree, right? Now the thing is, how do we approach this particular problem? So prerequisite for this particular video will be, please watch my video on finding the height of the subtree, height of the binary search tree, not binary search tree, height of the binary tree, right? So please refer my the video that I have created on finding the height of binary tree, because for this particular problem the algorithm that I'm going to use is exactly same as finding the height of the binary tree. So I will first of all write a code for finding the height of the binary tree, and then I will explain by making a slight changes how this particular problem can be solved. So let me just quickly write the problem for finding the height of the binary tree. So I hope you have watched my video on that topic, finding the height of binary tree. So that particular topic I will not be explaining much in detail in this video, okay? I'll just give you an overview. I'll be giving more intuition on how to solve this particular problem. Anyway, so this is the function is balanced that will check whether my tree is balanced or not, the root node that I've received here. So what will I do first thing? So remember, my algorithm says that first of all write the code for finding height of binary tree. How do we find the height of binary tree? So that is the code that I'm going to write. So first of all, what I'm going to do is I'll check that if my root equal to null. So since this particular function is balanced, is going to check whether my tree is balanced or not. What if it receives a root node? So there should be a base condition. What if it receives a receives a null? That is, if the tree is empty. What if the tree is empty? So if the tree is empty, it clearly indicates that definitely the tree will be a balanced. Okay, so we will return true. So if the tree is empty, we will return true. else we will think about checking whether the tree is balanced or not, right? So else we will just call the function check, or better write height. Okay, because I said you that I'm going to write the function for computing the height of the binary tree. So integer h equal to height, and I'm going to pass the root node. So you remember this particular function, what will it do? Height root, this will be a call on the function height, and once this function has successfully executed, it will return the height of the binary tree. That is what I have just written here. So for that particular reason, I am going to write the function integer type function height, and what it is going to receive? Tree node star root, right? So I hope you are familiar with this problem, how to find the height of the binary tree. So let me just write the code. So the code for finding the height of the binary tree says that you will first of all check that if root equal to null, what do? We return 0. No doubt with this. Otherwise, what do? Is basically we compute the height of the left subtree. So integer lh is equal to nothing but compute the height of the left subtree, that is root left, and also compute the height of the right subtree, that is height root right. So compute the height of the left subtree, compute the height of the right subtree. And what we used to return? We used to return 1 plus maximum of the left height comma the right height, right? So I hope you are comfortable with this particular problem of finding the height of binary tree. So far what did I write? I just wrote the function of computing the height of the binary tree. So no doubt with this, right? So now I want to actually I just want to actually find out whether this particular tree is, you know, balanced binary tree or not. How do we check that whether it is a balanced binary tree or not? As I said you, the condition was that for every possible subtree, right? For every possible subtree that you are considering, the absolute difference between the left height of the left subtree HL and height of the right subtree should be less than equal to 1. So for this particular reason, what will I do is whenever I compute the height of left subtree and right subtree, whenever I will compute the height of left subtree and height of right subtree, I will keep track of the maximum difference observed. Please keep in mind, I will keep track of the maximum difference of the left height and the right height observed. Whichever difference is maximum, I will be just keeping track of that maximum value. I hope you're getting the point. So what is the concept? The concept is throughout the execution of this particular problem, I will be keeping track of, you know, the difference between the left height and the right height of absolute difference of every possible from every possible node, and I'll just update my maximum value. At the end, I will check whether my maximum value is greater than 1 or not. So if the maximum difference is found to be greater than 1, it clearly indicates that there was at least one instance somewhere in the middle or somewhere inside this tree where the difference between the left subtree and right subtree had exceeded 1, and we know that once this condition becomes true, we will immediately conclude that my tree is no more balanced binary tree. Okay, so let's keep things simple. The concept is keep track of the maximum value of this absolute difference between the left height and the right height. So where am I calculating the left height and right height? So this is my left height, this is my right height, right? So I should now calculate the difference, okay, and update my difference. Mx equal to maximum value of the difference of, you know, absolute difference of left height minus right height, comma mx. So mx is what? Let us suppose initially mx is a very small value. Mx is equal to integer mean. Okay, so this variable mx will keep track of the maximum value of the difference, maximum absolute difference observed. So you can just see this particular line here will just every time check and update the mx to the maximum of the mx value or the absolute difference. Whichever is maximum will get updated here. Getting the point? That's it. So you can just see that how this function is actually helping me to solve my particular problem. This particular problem is basically finding the height of the subtree, height of the binary tree. This problem is basically finding out the height of the binary tree, and this line here is just using this particular function to do it, to meet its purpose, right? How? Let us see. Now you know when the problem will be successfully executed. Okay, when the program will be successfully executed, when this function will be successfully executed, okay, what will it return? It will return the height of the tree. So the height of the tree will be returned in the variable h, but I don't have to do anything with the variable h. This was not of my interest. My interest was just to run this particular program of height wherein I will just be using this particular line to keep track of the maximum value of the absolute difference. So my concern is about mh. So what will I do? I will say, since mh is a global variable, I can say that if mh is basically less than or equal to 1, which means the difference observed, maximum value of mh that you observed so far after completely executing the tree and after completely going through all possible subtrees, is less than or equal to 1, you will return what? True. Return true means your tree is definitely a balanced binary search tree, right? No doubt with that. Else what will you return? Else we will return false. You know why? Because if your difference, if your maximum value of this mh, which was keeping track of the absolute difference, has exceeded 1, which indicates that definitely there was a one circumstance where the difference between the left subtree and the right subtree has exceeded 1. That is why mh has exceeded 1, isn't it? So if it exceeds 1, we will return false, which means it is not a balanced binary search tree. Sorry, not a balanced binary tree. Okay, please consider it to be a balanced binary tree. I'm just saying it balanced binary search tree. I don't know why, but it is a balanced binary tree. So if the difference exceeds 1, we will consider it to be false, right? That is, it is not a balanced binary tree. Oh, that's it. So let us run the code. I hope you are not doing any silly mistakes. mx, okay, mx is not declared, so integer mx actually, right? Sorry for that. All right. If mh less than equal to 1, what is the issue? All right, integer h is this. If mh, okay, why mh? It is mx actually. I'm sorry for that again. Semicolon missing. Alright, the test case has passed, and you can definitely see that the problem has also successfully executed, right? So, and you can see that it is basically runtime is 8 millisecond and it is faster than 90.919% of submissions. Anyway, it was very good approach to solve this particular problem, using recursion and while finding the height of the binary tree. Now, in case you are interested to see the working, so I'll just continue the video rather than completing it here. I will show you how the problem is actually working, right? So if you're interested, you may continue watching. So let us see how the problem has actually worked. So for that, explaining that, what will I do is basically I'll consider an example. So let me take an example. So suppose, so I had used an example here. Yeah. So this is the tree that I'll be using to explain you the concept. So let me just increase the size of the screen now. I wonder if this is a full screen. Anyway, so let us continue. So remember, we have a tree 75. Okay, we have a tree 75. Any node, suppose we have 100. We have here 49. Values does not matter because here we are just finding the height. 87, 8, 11, 50, 63, 100, and obviously this is the left subtree 26. Now see, initially what will happen is balanced will receive the root node. When isBalanced function receives the root node, we know that root is equal to null, that return true. But obviously the root is not null, which means we have something in the tree. So definitely we will start doing what? The else part. The else part here says that call the function height, which means compute the height of this tree. So we are interested in computing the height of this tree, right? Because the height function is called. Once the height function is called, we are basically interested in finding the height of this subtree. Now how will it work? So first of all, it will check that whether root is null. Definitely root is not null. So if it is not null, it will just keep on calling root left. You see, height root left. So what will be done? So initially this was my root node, right? So it will call root left, which means it will focus on this left subtree. So let me write like this. So it will focus on this subtree where this is the root now. Now if this is the root, again it will call what? Root left, because this is a recursion. So again it will be doing a call on this subtree. Now this is the root. If this is the root, then what will it do? It will call a recursive call on the left subtree, which is 63. And again this is the root now. So it will do a recursive call on the left subtree, but here the left subtree is nothing but null. So what will happen is, here from the left side, what it will return, what will it receive from left side? You know that if the value of root is equal to null, the integer lh equal to root left. So root is this, its left is what? Null. So we know that if it is null, it will return 0. So which means the value of lh, if you are standing at this node, the value of lh that you received is 0, the value of rh that you will receive is 0, because our right subtree is also null. And remember, we have already declared mx to be very small value, extremely small value, mx equal to minus, suppose, large value, negative of a very large value. So now right now my mx will be updated to what? The absolute difference of these two. So 0 and 0 is 0, and mh is very negative, so which is bigger? 0 is bigger, so this will be updated to 0. Done. And it will return what? 1 plus the maximum height of the left subtree and the right subtree. So left is 0, right is 0, 1 plus 0 is 1, so 1 is returned. So right now I am back to this node, so I am standing at this node, this is my root node, and what is the height of the left subtree? Right now I received as 1. So let me just drop these things. So remember, the height of this left subtree it has received is 1. So after it has received the height of the left subtree, we know that again it computes the height of the right subtree, root right. So root right, again height will be this particular function will be called. Now this node will be considered, this is the root node right now, 100. So its left is 0, right is 0. So LH will be 0, RH will be 0. The maximum of 0 minus 0 comma 0 is again 0 only. So no changes observed here. Now it will return what? It will return 1. What is the height? 1 plus maximum. So 1 plus maximum of this I got 0. 1 plus 0 is 1, right? So 1 was returned. Now you are at this node. So it has received from left node 1, from right node it has received 1. So LH is 1, RH is 1 for this particular node. LH is 1, RH is 1. Mx is equal to maximum of the absolute difference of left height and right height. Left height is 1, right height is 1. Absolute difference is 0. Maximum value right now is 0. 0 comma 0, maximum will be 0 only. It remains 0. And it will simply return what? 1 plus the maximum of the heights. So 1 plus maximum of 1 and 1 is 1. So it will return 2. So I hope you are following the points. So what does it say? It says that it will return what? This node will return 2. Which means the height of the left subtree of 100. Now right now 100 is a root node, right? The height of the left subtree of this 100 is 2. Now basically it will compute the right side, because left height is already computed. Now it will compute the right height. So that is the height of the right subtree. So for that, this particular subtree, there will be a recursive call. Again, this 8 node, the root 8, when root will be pointing to 8, this will be doing a recursive call on the node 26. Again 26 we will be doing a recursive call, but here you will find out the left LH is 0 and null, RH is null. So LH will be equal to 0, RH will be equal to 0. Maximum of this is 0 only. Absolute difference will be 0 only, and absolute difference and mx value will be 0 only. So no updates. Instead it will just return the height. The height is 1. 1 plus maximum of this is nothing but 0. So 1 will be returned. Which means that this particular node 8 has received a value from the left subtree, which is nothing but 1. Right now it received 1. So the left height, now if you are considering this node 8, right now I am standing on the node 8, the value I received from the left side was 1, which means my left height is what? 1. So what is the value I received from left height? Left height is 1. Right height will be what? 0, because you see its right height is null, its right child is null. So if right side is null, which means what will be the value returned? 0. So RH is 0. So what is the absolute difference of LH and RH? 1. So 1 comma mx value right now is 0. So 1 comma 0, what is the maximum value? 1. Which means right now I observed a maximum difference of 1. So I updated this mx to 1. Where did I observe? In this particular node, isn't it? So right now again this will be returning what? The height of the tree. So height of the right subtree will be what? 1 is maximum of left and right is 1 plus 1 will be 2. So if you consider the node 100, I am back into node 100. So the node 100 is considered to be the root node right now. From the left I found 2, from the right I found 2, which means the height of the left subtree for this particular node, the height of left subtree is 2, right subtree is 2. Difference will be what? 0. 0 comma maximum, 0 comma 1, maximum will be 1 only. So 1 will be remaining here, no updates. Instead what will be returned? 1 plus maximum of left height and right height. So 1 plus maximum of 2 and 2 is 2. So 1 plus 2 is equal to 3. 3 will be returned. This is nothing but the height of the left subtree. I hope you are following the points, because this problem is nothing but finding the height of the binary search tree. So I found out the height of the left subtree for this particular node, because I am back to this node. I am standing here. If I am standing here, from the left subtree I found out the height to be 3. Now this will be doing a recursive call on the right subtree, because the left subtree height I have already computed, because I have received the value from left side. After you receive the value from left side, now you will just call the function on right. So on the right side, what did you call? So remember, from left side you got 3. Right side, when you do the call, root is on 49. This will again do a recursive call on the left part, that is 11. This will again do a recursive call, but again you will find null left, null right. So again no updates here because the difference will be 0, and 0 and 1 maximum will be 1 only. This will just return 1. So height of the left subtree of this node is 1. Again for this right node, again there will be a recursive call on this node, and this node again left is null, right is null. So again this will be returning 1. So if you consider this node, because I am back on this node, the difference between the left and right is 0. 1 minus 1 is 0, and obviously 0 is less than 1, so no updates will be taken place. What will it return? It will return 2. So right height will be returned will be 2. Right now I am on this node. From left side I received 3, from right side I received 2. The maximum value of 3 and 2 is what? Absolute difference of LH and RH will be 1. So 1 comma mx, that is 1. Maximum will be 1 only. 1 only is keeping here, 1 only is kept here, and you can just find out that what will be returned, that is 1 plus maximum of these two. So maximum of left subtree and right subtree is nothing but 3. So 1 plus 3 is nothing but 4. This will return 4, and 4 is nothing but the height of this subtree. 4 is nothing but the height of this subtree, right? 1, 2, 3 and 4. So that's it. So you can see the height of the subtree will be returned and stored in H, but I have nothing to do with it because I just wanted to keep track of the maximum difference observed, and maximum difference is nothing but 1 in my case. And again I will be checking that if mx is less than or equal to 1, then we return true, that is it is a balanced binary tree, otherwise not a balanced binary tree. And that is what we observed, and the problem has successfully been executed. That's all from this side. I hope this video was helpful. In case of any doubt, please feel free to put it out in the comment section, and just like, share and subscribe. And one more thing, this particular problem was also available on Geek for Geeks. You can see I actually wrote the same code on Geek for Geeks also, and this logic actually due to some issues was not running in this particular platform. However, the logic is exactly same. The same code I have used for on LeetCode platform also. Here it has successfully executed, and here I don't know why it is giving some issues. So anyways, just for your information, so you can see just now we showed that this tree is basically a valid one, so it should return 1. My code should return 1, but I don't know why this platform, in this platform my code is returning 0. Anyway, I hope this video was helpful, so please like, share and subscribe. Thank you.